Question 7 on the practice final reads that we're given a positive charge Q sitting between two conducting planes that form an angle of 60 degrees between them. So we have the charge Q, that's a distance d away from one of the planes, we'll call that the horizontal plane, and it's distance a away from the angle, the plane that's on the angle of 60 degrees. We want to, for part A, we want to draw the image charges of this configuration, being clear about whether or not they're positive or negative and what position they're at. So we can see right away from this problem that it's going to be similar to the method of images problems that we've seen in some of the previous videos. And of course, if we want to find the potential in the region between the two conducting planes, this will be challenging if we only look at the conducting planes and the charge positive Q. Because of the charge distributions on the conducting planes, we're not sure what these are, so they would be challenging to find first, and then we'd have to use those in conjunction with the charge Q in order to find the potential in this region. We can do a simpler method by instead looking at image charges and determining the potential by these image charges, and this will be, because of the uniqueness theorem, the potential that we would like to find in this region, and by a simpler method. So the problem 7, part A, asks us to just simply draw these charges. What I like to do for these problems is essentially extend the planes that I see here already in the problem, and then due to symmetry you can kind of see that there's a gap here, right? So right away I'm going to fill in that gap, and I'll explain why this is the correct setup. So essentially we have, the way I like to remember it, is the number of charges, total number of charges in our configuration, including the image charges and including the charges that are already present, is equal to 360 degrees, the total circumference around the central point here, divided by the angle between the planes. So in this case, the number of charges we want to see, 360 degrees divided by 60 degrees is equal to 6. So what that means is that the total number of charges that are going to be present in our configuration, both image charges and the real charges, is 6. And you can kind of use this setup for any sort of angle between the two planes. So if we consider that we have simply one horizontal plane, we can argue that the angle between the planes in that case is 180 degrees, in which case we have 360 over 180, which is 2. And that's what we've seen in the classic method of images problem, where we simply have a positive charge above a plane and we see the image charge below. So any sort of angle between the two planes that gives an integer number of charges, that will be the correct setup in order to determine the potential in this region. So now to continue on and see where these charges are situated and whether or not they're positive or negative, we can simply extend what we see here and mirror across the planes. So in this case we have a distance a away, and we'll see this a here as well. And then we'll have a distance d to supplement that and one charge here. And then of course we'll mirror across here and we'll get d as well. We'll go down here and have a. Again we'll have a. Here we'll have d. Here we'll have d. And finally we'll have a, and d. And this gives us 1, 2, 3, 4, 5, 6 total charges, which is what we expect. And of course we see the kind of mirror pattern where we have a mirror to a, d mirror to d, a to a, d to d, a to a, d to d. And that's how you can kind of know that you have the setup correct, because any sort of angles that you make with your planes, you're always going to have this kind of oscillating pattern of flipping across each or mirroring across each conducting plane, which is why I drew this third plane in on that angle. So of course the angles between each of these planes will be 60 all the way around to form the 360 degree circle. Now, how we know whether or not they're positive or negative charges is, again, we do this sort of going back and forth or oscillating or flipping of the charges. So we initially saw that when we have the positive Q above a horizontal conducting plane, this charge here should be negative. But then when we mirror across this plane, we should get a positive. And then we'll mirror again, get a negative. Mirror again, we'll get a positive. Mirror one more time and we'll have a negative. and if we mirror the last time, we should get the positive charge that we started with. So as long as you have this plus minus plus minus plus minus pattern of going back and forth, and always in a situation where you never have two charges of the same sign next to each other, then this will work out and you'll have your diagram like so. Of course, I'm not a really good artist, so you can see that if you were to really draw it out with correct angles and correct distances, you would have the equal separations between them, everything would be at the correct angles, and you'd really be able to see that this is the kind of diagram setup that you will get. So that was part A. Part A just says draw these image charges, clearly label them, and clearly label the spaces between them. So I've done that here for part A. Part B asks what is the magnitude of one of these dipoles? And of course we know that the magnitude of a dipole is just the charge times the distance between them, between the two charges, which in this case we're going to have two different ones if we consider the distance A or the distance D, and our charge is just Q, and our distance between them in either case will be either 2A or we'll have Q times 2D, depending on whether or not we're looking between these two charges or these two charges, depending on the separation between them. So that's part B, is just find what is the magnitude of one of these dipoles. Part C asks what is the total dipole moment. I'll squeeze that in here. The total dipole moment is just the sum of all the dipoles. Now in this case, because we have a kind of equilateral triangle set up, and we'll have three different dipole moments kind of pointing in different directions. So if we consider the ones between the two charges with the separation A, we're going to end up with one dipole like so, and then the other one like so, and then this one over here like so. So if we add these three dipole moments up in a vector form, of course we have this one here, and then this one here, and this one here, and we'd get the same setup for the distance D between these two charges. You can see that because we have this equilateral triangle kind of form, all of this will sum to 0, because the components in the x and y directions will exactly be equal and opposite in magnitude to become a total sum of 0. So the total dipole moment is just 0. And finally, for part D, we have how would the potential V depend on R for R much greater than A. So if we're looking at the potential V in this region over here, and we're at some position R much greater than our distance A away from this plane here, we'll see that, of course, as we move farther away, we're going to have the potential fall off as either a monopole, dipole, quadrupole moment. In this case, because our dipole moment is 0, we end up with the next term in the sum, which is the quadrupole moment. So we have this falls off as a quadrupole. And of course, the potential V for a quadrupole falls off as 1 over R cubed. And that is the answer for part D. So to quickly sum up the video and talk about question 7, which is the method of images problem, we initially start by drawing our diagram where we consider the angle between the two conducting planes, which gives us the total number of charges that we need to include in our diagram. We can look at the separation by mirroring across each conducting plane as we move around. And of course, the charges, whether or not they're negative or positive, will also depend as we mirror across the planes. Part B asks for the magnitude of the dipole moment between some of these charges. We can either have a 2A or 2D dependence, depending on not we're looking at the separation between two charges of 2D or of 2A. If we look at the sum of all of those dipole moments, in either case with the D or the, I guess these are opposite because we go from negative to positive, but either way it's going to sum to 0. This total sum will be 0, so the total dipole moment of this configuration is 0. As you can see here, the vector sum altogether. And then what that means is that the next term in our sum of our potential that we're considering will be the quadrupole moment, and then the potential V will fall off as a 1 over R cubed. And that is the answer to question 7.